Hi, I'm Rich with insideHPC. We're here at ISC 14 in Leipzig, Germany, and we're here at the Intel booth. And I'm here with Hans to look at deep and deeper applications. So Hans, what are we looking at here?
So this is a set of scientific applications we are using to actually validate our deep architecture. Well, they come from several fields of science, actually with a connection to everyday life. It starts with life sciences, simulating the brain activity, eventually the full human brain, well, maybe in 10 years. Okay, we have theoretical physics, this time high temperature superconductivity, so you want to know which substances are really promising if you want to have room temperature or close to room temperature superconductivity. We have a very complex computational fluid dynamics code here, and this is being used in aircraft and helicopter engines, really optimize those. This is an astrophysics code that predicts solar storms that hit the Earth. There's a climate code that couples climate simulation with actually simulating the atmospheric chemistry, so you can track what pollutants actually do to the weather and to the atmosphere. And finally, we have an industrial code for seismic imaging, which all companies use to actually find out how the various strata in the Earth are oriented so that they can find places where they could find, well, where you would expect oil or gas. So these are these 6 that we use for the DEEP project. All of them have been ported to use the DEEP programming model, and well, once we have the test system built up towards the autumn, well, we will really get performance results here. And in the meantime, a sister project has started called DEEP ER, which uses a little bit more advanced technology than DEEP. Well, there are 5 additional applications. Again, one from life sciences. This time, we're actually simulating what happens to human tissue if it is exposed to electromagnetic fields or radiation. We have another seismic imaging code, again, used by all companies, this time a different algorithm, a little bit more novel algorithm. We do have an earthquake simulation. Well, this is trying to find out how the Earth is structured.
Yes.
And this is simulating what happens if, well, you get an earthquake, which of course is very relevant and interesting. And this one has, well, actually today won the prize for achieving more than a sustained petaflops, which is really, really a cool
That's
result
exciting.
from LSZ.
Yeah.
Then there's astrophysics, in this case, a code that would actually process radio astronomy data from many thousands of little telescopes. And finally, there's QCD, quantum chromodynamics, and well, these guys are still trying to find out what holds everything together.
Yeah. So a very broad range of real science that people are trying to solve today, and applying that to a new potential architecture that could change how they do their work, maybe.
So the work there, the way we structure the work is that we have the experts in the applications, and we have a support team, again, from some of the centers that work there that help them to find out how to change the applications, how to improve performance, how to avoid mistakes. So it's kind of a joint action between computer scientists and the domain specialists here.
Okay. And then how do you model this? Do you have it hooked up to a big array of Xeon Phis and Xeons and seeing how it maps? Or?
Well, we use existing Xeon clusters as one of the porting targets, and we use some Xeon Phis also to find out how the performance there is. And then you can, well, predict where you stand. And once we have the system fully working, well, we will verify it. Also, we have some interesting performance prediction technology here by Barcelona Supercomputer Center that we're also using.